Okay. All right. So we are going to start with 3 formulas we know, and we're going to make a new magical formula. All right. So we have average velocity is x minus, and I write it sometimes different. Remember, like x2 minus x1, final minus initial. Right now I have x minus x naught. I think that's what your book does. I'm not trying to be more complicated, but there we go. That's my one color. Then I'm going to get another color and write another formula that we now know and love, and that's an A formula. Acceleration is v minus v naught over t. All right. And I'm going to leave this marker handy. And then I'm going to go for a third formula over here, another average formula, and that is if you have uniform acceleration, then velocity, some people tried to use this yesterday when they did not have uniform, by the way. If you're going 40 miles per hour for an hour, and then 80 miles per hour for 8 hours, can you say your average between those is 60? No, because you're not doing for equal amounts of time. So unless you have uniform change, you can't use the add them up and divide by 2 method. Okay? This is only for uniform acceleration. Okay? So some people kind of cheated on that. Okay. All right, so here we have these 3 formulas, and I'm going to take, well, what do I want to do? I'm going to take my first one. Whoops, that means I've changed color again. And I'm going to write it, I'm going to solve for x. Because many times x, kind of our new location, can be kind of thought of as distance if our initial point is 0. So I'm going to solve for x. And if I'm going to solve for x, I'm going to move my t over to this side and include that. So I'm going to say x naught, my initial position, plus my average velocity times time. Yeah? All I did was switch around. I'm going to do the same thing now. Oh, I want to get things interesting because I want to turn these all into one formula. And so I want to, what do I want to do? Which way did I want to do this? Hold on a second. I'm going to take and I'm going to take and get rid of the average velocity. And I'm going to do that by putting this in right there. Okay? So I'm going to write x equals x naught plus, and I'm going to substitute in my blue. Look, it's going to be all pretty. Okay? All right. Now, I want to replace a v. How can I replace that v? Is I can use this formula if I solve this for v. So can I, just like I did this one, can I say v equals here? V equals what? Can I multiply these two and put this with it? So equals v0 plus at? Yes? Okay. So what am I going to do now? I'm going to take, right, this part and put it in v. Okay? Rewrite it. X equals x naught plus, oh, Lordy, v0 plus over 2, but replace v0 plus at. Yep. All right. Now that looks kind of ugly right there, so we are going to do your mathy math stuff. So we're going to do, what do we want to do? Let's distribute, what do I want first? What did I do? What did I do? Let's distribute, you want to distribute the t? I don't know if I did. Oh, let's add those together first. Okay, I'm sorry. So we have my x naught plus, let's add those together. So v naught gives you? Okay. Okay. And two things are divided by 2, right? So what can we do? What do you want to do? Let's leave it for a moment, okay? And then we still have this times t. All right, now we can distribute the t, right? And if I distribute the t, right? What are we going to have? I can distribute the t. So I have 2v0 t plus at squared over 2. Finally, sorry, I'm going low. I'm going to go high so you can see it. So what are we going to have in the end? I'm going to have x naught plus, can't these cancel for this part? So we have v0t plus, but this 2 still has to be, at squared still has to be divided by 2. So usually it's written like this, 1/2 at squared. And what does this all equal? Because it's an equation, what we started with. We were looking for x. Here is our new magical formula, okay? And what does this allow us to do? This allows us to answer the Fluffy the Cat problem in 1 step instead of 3. Do you remember when you had a question about something was moving, it moved some distance with an acceleration, and I want to know how far did it move. You knew the acceleration and at a time. But you had to first find an average velocity to find distance. This is all worked in. So what does this tell us? Well, this part obviously is your new position. This is your original position. Where do you think the original position in a lot of problems is? 0. Lots of times this just kind of goes away. Or, you know what we do? Sometimes we move this to this side, and if we move it to this side, what does this become? Delta x. So you could have just delta x and eliminate that quantity if you want. Okay. What does this part tell us? What is initial velocity times time equal? Equals a distance. What distance is it, though? Initial distance. What does that mean? It means the distance you would have gone if you didn't what? If you didn't accelerate. Do you realize? Look at, well, no, it's not really here. So it would be this, right? It would just be a velocity times a time. And so it's, so I'm going to label that. Distance or how do we say, displacement, I guess we'll say, if not accelerating. How much you would have moved if you didn't speed up or slow down in the process of moving that some distance. What do you think this part, so that's that, what do you think this part must tell us? The distance you, or displacement, because you're accelerating. How about if I say the extra displacement due to acceleration? Now, people go, but it's not always extra. When would you move less than you initially expect? If you're doing what? Decelerating. If A is negative. So extra, or less. Yeah, what's the opposite of extra? I'm not sure. Anti-extra? Okay. Okay, lextra? Okay, less than extra? I don't know. But, so, when you solve this equation, really do it in 2 parts, please. Solve for this number, inspect them, and then add them together. And add them together would mean maybe take away and the number becomes smaller, or add them and the number gets bigger. The answer should be bigger than how far you initially go if you're accelerating, and the overall displacement should be less if you're decelerating. Okay? I will have later people do problems where we throw a ball in the air and they are sloppy with their numbers, and they literally say the ball goes higher because of gravity. See, and then when you do these in parts, you might go, oh, should my ball go further because because I'm throwing it up? And you go, oh no. But if you plug it in all at once, many times people you lose sight of what's going on. Okay? You shouldn't lose sight of what's going on. In fact, when I grade papers, the chance of partial credit really depends on whether you had a reasonable answer. Okay? When you concluded something, okay? And in our problems from yesterday or the day before, if you thought Venus Williams takes 3 seconds to get a tennis ball across the net, not reasonable, okay? Here's another one from yesterday. If a bird can fly 25 kilometers per hour, it's not going to take more than an hour to go 14 kilometers, which is what some people said, right? If you can do 25 in 1 hour, right, your expectation of your answer when you have a number less than 25 and I want to know time, should be less than an hour. And if you don't have that, you're missing that reasoning ability, okay, and keeping things in a perspective. One way helps is to break an equation like this into its parts. Enjoy that you have the equation, but to be able to break it up. Okay? All right. That's what we got.